The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The broadcast is now starting. All attendees are in listen-only mode.
Good evening, everybody. So today we will look into the accelerated tensor. So first we will look into the data pipeline. So we have mentioned that tf.dataset or tf.data, that particular class will give you the flexibility to maintain your data flow pipeline. Right? And different strategies we will see. Also, so before going into that, of course, we will see how to create the models, the three different ways. So the three different ways I mentioned in the last class, that you will have the sequential way, which is the best way to start for the beginners. It is very flexible, and if you want to have more control over definition of the model, then you go for the functional way, or you can go for the subclassing APIs. So these three ways we will talk about. Then we will talk about the data pipelining, accelerated data pipelining mostly. So how you can actually define the pipeline so that your data bottlenecks, all the data bottlenecks from different point of view, maybe processing, maybe opening the files, reading the files, different pre-processing you might be applying. Also, you might be reading data from, let's say, remote sources, right? Let's say from S3 you are reading the data, or maybe from Hadoop cluster you are reading the data. So all these ETL pipeline, the extraction, the transformation, and the load. So all these three pipelines, how you can maintain very effectively to accelerate the modules that will be working. And also we will talk about next the distributed training, which is very interesting, because here you will have many flexibilities. That also we will see. We will defining the different distributed strategies very easy, but you need to understand what is the particular environment you are working in, and that way you will be actually able to efficiently use those APIs or higher level abstractions to define what will be the distributed strategy for your particular model train. So let's go ahead to see these three APIs. That, as I was mentioning, that you have the sequential API, which will have particular one input. So maybe this is an input tensor, or multi-dimensional it may be, and you will have one output, which is again one tensor. And in the functional API, you will have these inputs and outputs, but you have, let's say you have multiple outputs. You can see from these two layers you have multiple outputs, and then you are concatenating to get one. So this is just one use case. You can have any where in between. You can have multiple inputs, multiple outputs, multiple input, single output, and single output, multiple, single input, multiple output, and so on. And in subclassing, you will have to use keras.model. So this is your superclass, and then you will define your layers, and you can connect them as you have done in Python. So mostly we'll focus on the functional API because this is a bit tricky to work with, but once you just understand it, it's very easy to use it in cases like where you will be doing some transfer learning maybe, or maybe multi-class or multi-stage classification. Okay, so or maybe working with multiple heads of classification or prediction. So different use cases you can use this function API, and this is very useful. And most of the cases people use TensorFlow just for functional API. So, quick overview of the sequential definition of the model that you have seen in the last class, that we have defined one sequential model from the keras.model and model.add. Then you have different layers, different defined, and like dense layers. You have flattening, you have convolution 2D. So all these things are there. Here we are using one dense layer, two dense layer, and three dense layers. Then we are actually, this is the output dense. So this is the output 1, and this is the output of this layer is 4. This output layer is 4. But remember, here we are not defining any input layer. So only the hidden layers that we are defining, and then we are getting the output, because you have only one output and one input. So you do not need to explicitly define the inputs. And just in the compile, you just can mention the which loss you will be using, optimizer you will be using, and just hit the feed, and it will do the training with this number of epochs and with this vaccines. So this is the naive way of defining one model in sequential manner. But of course, this will suffice for your, let's say, most of the training models that you'll be working with, right? But we want to go forward with some bit advanced technique with this functional API. Now let's see the layers first. Okay, so layer 1 we are defining now. So here all these layers that we have defined here and add. So model.add this dense layer, this dense layer, and this dense layer. So all these, whatever we are adding, they are making one stack, or let's say completely one graph. And then, so this is a complete data structure itself. Okay, so you do not need to worry about what you are getting in between, right? So this is a complete set. And when you are defining the models or model layers in the functional API, so in the functional API, you need to have the layers. Okay, so dense layer, convolution 2D layer, so any layer that you might have. Now here you see we are explicitly defining the input. So input layer, we are defining, let's say one input will have this shape and with some data, I don't know. So this is just the representation. We will see one such use case and in the end of this session. But let's define the layers first. So layer 1, layer 2, and output layer. So these three dense layers we have defined. So now you see that this output. So these are the just the layer definition. Now these layers are essentially functions which are callable. Okay. So we are calling this function with input layer. We are calling this function with layer 1. So layer 1 is essentially the definition or output of this particular layer, right? So from the previous layers. Now we are calling this layer with layer 2, which is the previous layer. So now you see that we are defining these layers, but we are calling them with the inputs that we are giving. So for this case, we are giving input layer, which is actually we have defined the input as, and then here we are using layer 1, here you are using layer. So this definition or this kind of just simple tweak, calling of these functions with these parameters or input layers or output layers, and output layer will essentially be the output of your internal, and then you can do the define the model. Okay, so model equal to model, and you define with this input and output set. Now, as I was pointing you towards the flexibility of using functional API in the cases where you will have multiple inputs and multiple outputs. So here you can define a list of input layers. So if you have different inputs, let's say 2, 3 inputs, then you can define list of inputs, and as output, if you have multiple outputs, you can have multiple outputs. So basically one list you can create that multiple outputs you have. So this definition actually helping you to define one model with different inputs and outputs. And since each layer is callable now, you can use this layer in anywhere you can for your target model. Right? You can call with any. Let's say I want to call this dense layer with this layer 1. That also you can do. So you can connect this output layer to that layer. So however you want, you can do this. So this is the flexibility I was talking about for the functionality. And at last, you have the sequence. You have the subclassing way of defining. So this is the keras.model, which will be the superclass for this, and you will have the initializer. So same way you have defined for the PyTorch. Then you connect them, and then you define the model equal to this. You create the instance of the model, right? So simple, elegant, and you have different ways of defining models depending on your target model and the flexibility you want to have. You can use either one to create your model, define it. Okay, so now we will move towards the input pipeline definition. Data pipeline is very important, and when we are using tf.data, then a new world of input pipeline opens before you, because all the abstractions APIs are already defined. You do not need to worry about, and all these will work as your C++ optimized code in the backend. So the performance you'll get is very high. Let's define why we need actually the input pipeline, right? Input pipeline means what? You just stack one after the processes from different let's say track or different different layers of your input or output. Now here, let's say you want to train one data set, and that data set you want to load into your memory, right? So how you are actually doing? Reading the file, then loading that into memory. So before that reading also you have this open stage, right? You have to open the file. Let's say you are working with CSV or maybe a big JSON record, or maybe whatever it might be, right? So the entire data, let's say you have 1 TB of data, you do not have the size or the memory available to feed the entire memory to read and then process that, right? So data might not feed into memory, so you have to pipeline. The pipeline stages are like however you define the stages. It might be read, open, then load, read, open, process, load. So whatever the stages you can define, so different stages you can define depending on the requirement, and you can pipeline them, right? Now, so because in each stage you'll have some output, and you need to store that into it. And data might require also pre-processing, as I was mentioning that in that pipeline you might have some pre-processing inside. So before loading and after reading you might have the pre-processing. So you can pipeline that and efficiently utilize the hardware underlying. You can use the pipeline, and you will see how miraculously it will accelerate the entire process actually, of data loading plus training, because training on your GPU will wait for the data always, and it's quite fast. So you need to feed the data, right? And pipelining the data efficiently will help to accelerate. So let's see how to decouple this loading and pre-processing. So as I was mentioning, that inside your pipeline, you might have data loading and pre-processing, these two stages, and you can decouple them from the distribution of the data. So loading will be happening in the end, and before that you need to pre-process it. But how you can actually use efficient pipelining to decouple them and distribute the data for your model training, that we will see in the next. So these are common stages of pipeline: extract, transform, and load. So extract is essentially reading the data from memory and storage, parse the file format, whatever you want to do. And then, so reading data from memory or storage, that means maybe local disk or maybe remote storage or whatever. Okay? Transform is essentially, let's say you want to normalize your data or vectorize your data, or maybe shuffle your data, batch your data, right? All these are different transformations that you want to apply. Then load to the accelerator. So this is the load part where you will, so you have the memory hierarchy. So you want to load from your RAM to your accelerator in the end. So that is the last stage of the pipeline that we see here. So let's see the naive way to do this, right? So first you have opened your data record or file or whatever you have, and then you read, right? So let's say you have read this chunk of data, okay, depending on the size that you want to read into your memory, and then you feed that to your training module. So then you train it, right? And then again you read the data, and then again train it, train the data whichever you have read, then again read, then train. So this is the simple sequential way of doing things. This is so if you are not doing anything to make the pipeline available, so this is not pipeline yet. This is sequential, and so this is how it will happen if you do not apply the efficient pipelining that is available with your data. So this is the simple way of defining. So if you write the code, let's say this is your training training loop, right? So for epoch, for sampling data set, so for each data set you just do this training. So time.sleep is essentially emulating the training step. Basically, let's say I'm saying that wait for this time to see whether my data is available, right? So this is a simple example to emulate this pipelining process, which is referred to your TensorFlow.org guide data performance. You can go to this link and see the entire code here. But here we are showing you how to use this pipeline. Okay? So now this benchmark. Okay, we want to benchmark with the data set that we have created. Let's say artificial data set that we have created. Now, total number of epochs I want to run for 2 epochs, and it will iterate through the dataset. Again, this dataset is TensorFlow dataset, so it is iterable, and you can iterate through the dataset, and you can feed that into the training model. So basically, here you will have the training a forward pass and backward pass and update, right? So instead, for simplicity, we are keeping it wait. That's it. And at the end, you'll have this performance count. Okay, so just to see how much time it is taking. Now the thing is that here, this is the naive way of implementing your training module where you will have the dataset. So this is exactly replicating the process that you are seeing here on the figure. But what we want to have pipeline. Now you will see that the CPU is opening the file here and reading the file here and waiting for the training to be finished here, and then it will load again the data, and then again the training will start. Now these white blocks you are seeing here, the CPU and GPU is essentially waiting for the data and training to be completed, right? Now So read is done by, let's say, CPU, and train is done by your GPU. So reading here, CPU is waiting here, here, and GPU is waiting here and here. Similarly for this one. Now I want to have overlap. That means when the GPU is training, CPU was not doing anything. I want to pipeline it so that the next set of data will be read and it will wait for the training to be started. So basically, if you see that the training was done here and GPU was waiting for this short time. Earlier it was very large. Okay. Now the waiting time for the GPU is shortened. And then again, since the data is loaded here, then GPU can start this training, and again the data can be read by the CPU in this blank time or idle time, right? And then again it will start, GPU will start the training. So I can see that we are prefetching the data. So this is one way of arranging your pipeline so that the data can be prefetched for your CPU by your CPU to be available for the GPU to train simultaneously. And how you can do that? It's very simple. Just you call prefetch with this parameter tf.data.autotune. What is this doing? This is saying how many prefetches it will do while it is idle. So if you want to define one number here, 3, 2, whatever, depending on your environment, if you know your CPU well, if you know your GPU well, and if you know what kind of size of the RAM and size of the data you are using, you can define this number manually. Rather, you can take the advantage of tf.data runtime, which will define this auto tune by automatically setting, analyzing the environment and set this number for you. So that's the best way to do things. So this prefetching, you can reduce the idle time for the GPU and accelerate your training. Interleaving, if you have, let's say, different data sets to be read. So let's say here two colored reading is doing, but they are being interleaved. That means one is being done at the same time, and at the next timestamp, another one from the data set, another data set will be read simultaneously. So you can see that interleaving of different data sets you can do also. And this interleaving is essentially useful for the cases where you'll have the remote storage. So I mentioned before starting this interleaving and pipelining things that you need to know your environment. So when you are reading your data from your remote storage, there the bottleneck is IO bottleneck, because reading and writing will have different time from different sources you are reading, right? Now if you interleave, whatever is available, that will fetch the data, read the data. So that way, in that case, you will have accelerated training, and the idle time for the GPU will be very less. And if you were using simple reading with the IO bottleneck, then I mean it is horrible training. So and you can parallelize this interleave process. So dot interleave will actually help you to interleave from different dataset reading, and number of parallel calls, again you can define the number here, or you can use tf.data.runtime, and the autobeam attribute will actually fetch the number yours by the runtime itself. So you do not need to worry how many parallel calls will be there for this interleave. We can do parallel mapping. Now mapping is very important transformation that you will do mostly while doing or creating this data pipeline. So earlier we had open, read and train, but here we now have map. Now we want to pre-process the data before loading this. This is another stage in that data pipeline that we have introduced here. Now what we will do here, this is the naive way, the sequential mapping, where you just open, read, map sequentially, then train, again wait for the CPU to get the training is done message from the GPU, then it will again read the next set of data and blah blah blah. but I want this to be happening parallel, the mapping to be happening parallel. While it is waiting for the next data to be read and pre-processed, you see how much time it is waiting. I want to just reduce this waiting time, collapse all these rates, collapse the mapping, do the parallel mapping, and you see the waiting time for the GPU has been reduced to from this to this. You will have accelerated uh, you will have accelerated mapping again. Okay, okay. Sorry. So now how you will do that? You just call dot map. So basically this is for the map transformation you want to apply on your data set. And this is the map function. So map function is the transformation you want to do. Maybe let's say you want to increment your data before loading, or maybe you normalize your data by, let's say, dividing it by 255 as you have done for your images. That pre-processing you want to do with in this function, map function, any pre-process you do. But this is the simple way you will do definitely. But number of parallel calls, if you define it with the auto tune, it will just parallelize your reading, fetching, and mapping or pre-processing. Now remember, uh, uh, one very tiny details that we will add into the next section. Okay? When we will cache this. Basically, all the things we are doing here still now, it is just happening. How it will, how the CPU and GPU here, the CPU is doing the mapping and reading. If you are asking why not GPU is doing the mapping, or maybe for this case, also this case, parallel case or sequential case, GPU cannot do the mapping because GPU do not have the general purpose processing unit, right? So CPU has. So CPU can do the pre-processing. So there is no way GPU can do the pre-processing. So it can do only matrix multiplication or multi operation or graphics operation, ray tracing operations. So apart from that, it cannot do anything. So map you have to do inside the CPU. So CPU will do the mapping. So the map number of parallel calls you have to define. Caching is important because now I want to say that why you are applying transformations every time. You do the transformation, you transform all the data and keep it in the cache or memory or the file, wherever you want, with this cache function. That's it. So what is happening here, you can see that for this set of training, it is not fetching, not doing the read and transformation as opposed to the previous method, right? Because all your transformed data is inside your memory. Okay? So it is transforming all the data, keeping it in the memory, and it is not doing anything. That's it. So for the next epoch, let's say this is the epoch. For the first epoch, yes, you do the transformation and load the data. But since that was the time that CPU is taking to pre-process the data and load into your memory, and in the next epoch, it does not do anything. CPU does not do anything because the data is already present inside your memory. So then the GPU will just train. Okay. But one tiny thing again, apply time-consuming operations before cache, and apply memory-consuming operations after cache. So this is the thumb rule for caching. If you have very much time-consuming operations, you do before cache, because that way, in the first epoch, you will have bit performance here and there neglected, but once the pre-processing is done, then you'll have much faster training in the next epochs, right? But here, if you have this function, this transformation function, which is memory consuming, then you cannot do before cache because you cannot apply all the data to be stored in the memory by caching because it is memory consuming transformation. So you do that after caching. Okay, so this is the simple thumbnail you need to keep in mind. Okay, now we have scalar and vectorized operations. So now you can see here we are opening the file, reading the file, mapping the file. Now map is doing the transformation, and map is called after each scalar data. Let's say I want to normalize it. So each data will be called, then map function will be called, and then it will map, then next data will be read, next map will be done. So why do that? You can do only one map with all the batch of data but one time. That's how you will do that. This is the vectorized map. How you will do that? So this is the simple way of doing it, batching, because in the batching you will actually batch and then map, right? And you do the batch before mapping. Okay, so because now we are vectorizing the mapping operation. We are giving the batch of data to the mapper to get transformed. And you can see that all this waiting time for the mapping is in just collapsed, and you get very efficient timing for your CPU as well. Usage will be more, and the training will be faster. Now, all this tier data that we have talked about, but we have also mentioned that TFDS, which is the TensorFlow dataset, is essential to be used for your training, and it has a lot more predefined dataset that you can use. Like here, we are using, let's say, MNIST dataset that we want to use for loading and splitting train. So you use TensorFlow dataset. So TFDS module you use to load your data and batch it or whatever you want to do in the next subsequent processing. And to get more details, how you can use this TensorFlow dataset, you go to the link provided here from the TensorFlow developers, so you can see through the code complete training module for using the TFDS. Next, we will go forward with the distributed training. So, as I was mentioning, that it is very easy to distribute the training in TensorFlow, but why we are using that you need to know, because the environment you are working with, you need some enhanced performance in the end. But actually, you need to also know the environment that you are working with, right? So the ideal performance you want to get, let's say, very fine-tuningly managing the entire pipeline of your training, defining. So we were mentioning something about this line in the last class, that you can fine-tune or finely manage which step will go to which GPU that is available for your system. But distributed APIs, if you are using that, you will get out of the box performance, which is essentially kind of equivalent if you are doing that fine-tuning. What does that mean? That means that using this simple API, just one line of code, you can distribute the training, but you will get the same performance as if you were fine-tuning each step of your training pipeline. Now, how it is happening, we will not go into that details, because in the backend, as I was mentioning, it is called, the core is actually developed with C++, and it's very close to system. That language is very close to your system. So the performance you'll get with the C++ backend is much higher than Python, right? So that way, using these APIs, you will get the same performance as if you are fine-tuning. Now, using these APIs also is versatile in nature, because the same strategy you can follow for different architectures, different hardware, different APIs, as well as combination of them. Okay, so we will see a few instances of that. Now, distributed strategy essentially is the main class for that distributed strategy, and this strategy is used to distribute any model using Keras API or estimator API. Now, again, in the previous class, so you just follow the sequences. In the previous class, we have said that you can define your models using Keras API or estimator API, but estimator API is not being maintained nowadays, so you can use only Keras API for efficient distributed manner. Now, distributed my model is also possible using a customer training loop. This is very simple, and also to get much more flexibility. Okay? So you can make your layer, your library, your infrastructure distribute aware. What is distribute aware? We will see, but you can make your different stages of defining your model. You can define which will be the distributed aware uh, module for your case. So this is much more control. So TensorFlow is all about abstracting everything to opening everything to you. So that means high flexibility and high controllability. Okay, so both you can get. Make a new strategy. If you want a new strategy to distribute your training process, that also you can make it. And that is also quite valuable if you're targeting, let's say, multi-accelerator things. But again, some APIs are already there, which will help you to take advantage of different accelerators that are available in your system. Yeah, different API surfaces for each of the module that you will see now. Now, this strategy, that first strategy we will talk about is the mirrored strategy. So mirrored strategy is the multi-GPU all reduced sync training. So it is all about synchronized training. Synchronized training means each of the devices where you are distributing the processes will be locked and executed. So, and all the APIs are maintaining everything for you. You do not need to worry about the global interrupt lock. So, it is very efficient. So replicas of the variables that you want to distribute, that will be actually made replicas, and it will synchronize again at the gradient stage. So when you are trying to compute the gradient, then it will meet again, and so this is all stage where you are actually distributing your variables to or making replicas in each device. So basically, let's say you have one system where you have one CPU and multiple GPUs. You want your replicas, that means replica of the variables that you want to distribute, will be available to all GPUs. That is all. And in the reduced stage, you're actually synchronized, right? So this is all reduced, and sync is essentially doing in lock state processes. Variables are mirrored in each GPU, as we were discussing here. And all reduced, this algorithm will actually do the aggregation of the gradients. So how it is doing it? So let's say we have this one device and second device here. And first device we are giving the input. Here's the input 0 and another input 0, input 1. Now here we have the same layers A, B, A, and B, A. That is the backward pass, and this is the forward pass. Now I want to replicate the VA. So VA0 and VA1 has been, two instances have been created, which is replicated actually in the two devices here. Then the output for the second layer is VB0, VB1. Then we are doing the backward propagation. So now we want to have this VB0 and VB1 to be made in the middle somewhere where it will be aggregated. And again, so basically this is the reduced stage where it is reduced. The variables is, all variables will be reduced, and then it will be distributed again, and then again the gradient combination will happen, and again it will need to get the average of the delta, which will help you to improve the to update the weights for particular devices. So VA, del VA, which is computed here, will be broadcasted to all these GPUs here. So this is the synchronous training. So you see here each. So this is locked also. This process is also locked, and you until or unless you get this here, you don't know. You cannot do the reduced training. So this is the synchronous training. Now all reduced synchronous training, how you can define it, the strategy. So mirrored strategy, that means making replicas, replica of variables. How you can define? This is one way of defining. Strategy is equal to tf dot distribute dot mirrored strategy. Mirrored strategy is very simple function which will distribute your or mirror your variables to all the devices that is in. If you want to particularly define which are the devices that you want to work with, you can also give the arguments which are the particular devices, GPU 0, GPU 1 in this case. And also you can define which reduce algorithm will be used. You can define that in the argument also. These are the three ways to define the strategy. Once you have defined the strategy, you can go to your model definition and completion. This is the sequential way of defining the model that we have seen so far. And to add like these variables which are used in these layers will be distributed to your machines. If I want to specify that, we'll just wrap this with this strategy.scope. That's it. So you define the strategy, you wrap your entire training module inside the strategy.scope. So this particular block is under this strategy's scope. That's it, simple. And you will have the mirror strategy with all reduce. That's simple. And this particular block, which you will see in this red box, is essentially the distributed error box or distributed error block. So distributed error block, you can also define that you have seen so far. So this is the distributed error block, because now now the backend knows that this is the block where I will mirror the variables. You can have multiple worker, so that was for single worker and multiple devices. You will have multiple worker, multiple devices, and in this case, TensorFlow collective ops will be uploaded. Again, the thing will be synchronized in nature, and so workers will run in lockstep, and you will synchronize the gradients in each step. Okay, so each step will be distributed to multiple worker, multiple devices, whatever you define. So worker, which will do the things, okay. And this is again synchronous in nature. So how to define that? You want to distribute, use the multiple worker mirrored strategy. So this is coming under the experimental module. So this is just the experimental module, but it will be transferred to your mainstream module in any time. Okay, but you can use this tf.distribute.experimental.multi-worker mirror strategy to define one mirror strategy, which is will be creating one scope for your distributed module, which will be distributed to multiple worker and multiple devices. You can also define which backend communication will be happening. HCL you can define. Okay, right. Then you also need to define the workers, basically which will be the task type and the workers, and that will be given as JSON string form. Okay, so cluster, the specification for your nodes here. This will be the worker, and this will be. So this is the simple usage of a multi-worker mirrored strategy where you can have multiple worker working tandem in a synchronous manner. All the steps will be locked and executed. You can have all videos synchronized training for TPUs as well. So it's a bit tricky, but since through the Colab also you have seen that you have the flexibility to access GPUs. It is similar to your mirror strategy, but unlike mirror strategy, it will use cross replica sum to synchronize the aggregations from different nodes. One TPU is TPU, and many TPUs is called TPU pods. Okay? So you can have both. So how to define this strategy? So again, as I was mentioning that once you have defined this strategy, you can use strategy dot scope and define your scope. Again, here we will define the strategy and strategy dot scope. You will define your distribute error block. That's it. How you can define it? You can define your resolver, which is essentially transfer resolver class, and this will actually be using this TPU cluster resolver for the TPUs. Okay, so it's a bit tricky, but you can use these steps to use this strategy. Now, how you will get the strategy? You will just define to connect to the clusters, initialize the TPU system, and then use this resolver to create the strategies, right? So this is again coming under distribute.experimental module where you'll have this TPU strategy to be defined for your TPUs. And you can use this strategy using strategy.scope. So we have talked about synchronous execution where your workers are working in a locked state, right? What happens if your workers, let's say multiple devices you have in one system, they are not similar in runtime performance. Let's say some worker will do faster, some worker will do slower, and so on and so forth. So you will have different performance workers in your device or in your machine, and you can use parameter servers and workers in this case. Parameter servers maintains the global variables which will be actually synchronized and doing the aggregation. And worker nodes will again do the replication of the variables computing, and then it will send to the server parameter servers to get aggregated and get back. So parameter servers will take care of this synchronization. So these workers will be working in their own way. Okay, so this is a bit different from your synchronous way of working things. But once you have the APIs, you do not need to worry about anything. So the parameter server strategy we are defining it with, again, it is coming under distribute.experimental and parameter server strategy. So you can define it, and you can also define with parameter solver strategy with these two ways. Okay, so this is just the name that we are doing. Now, once you have defined it, actually you can use the strategy as a scope, and also you need to define in the JSON string format the workers, which will be the PS, the parameter servers, and which will be the worker. So these two definitions, if you just give in the configuration string, that's it. So once you have this definition for the tasks and the cluster, so basically what nodes will be the worker and what are the nodes will be your parameter server. So that's it. One more way of approaching is central storage. So central storage is basically the one node approach of parameter server 1, the PS worker strategy that you have seen. So this is asynchronous also, but we think that, so here we had multiple devices where we have defined which will be the parameter servers and which will be the workers. But here we are thinking from a single node point of view. In a single node, you will have multiple devices which are not exactly same in performance. So you can use central storage approach where one machine, multiple GPU will have one copy of each variable will be in CPU. So maybe CPU will be working as a parameter server, right? And one replica of the model will be in each GPU here. And because it might so happen that parameters, the number of parameters, this is another case where the number of parameters is getting exceeded more than the memory that is available for your GPU. So what you will do, because you are doing the replica, you are maintaining the the gradients, and then again you are sending back those. You are getting all the updated values, aggregated values again. So it might so happen all the embeddings may not feed your GPU memory. In that case, you can use your CPU to be working as that central storage, okay, and offload everything to your CPU and do release some of the memory pressure from the GPUs. So how you can define it? Again, it is very simple. Strategy equal to pf.distribute.experimental.central storage strategy, and that's it. So your one PC system will be working as your parameter server strategy, and you can use this strategy dot scope to define it. So these are the reference codes that is already implemented with the engineers from TensorFlow for getting to know more about this distribution strategy that is already implemented for several reference that you can look. We will go into now one demo for functional API to understand better some problem approach we will see. So what is the problem that we are referring to solve it with functional API? Mentioning I may have single input and multiple outputs, right? So one problem I am defining here. So you have seen the image dataset so many times for now, which is essentially the dataset for your handwritten digits, right? So from 0 to 9 we have digits, and all the images from different way of writing it is there. Now I want to I want to create one model which will classify first, of course, the digit, whether the digit is 5 or 6 or 9 or 10 or 0 rather, and another head will predict whether this is being written in left hand or right hand. Okay? So this is the problem statement that we are targeting here. So again, one single input, one image you will give as input, and it will give two outputs. What is the number? Essentially 0 to 9, and whether the number is written with using right hand or left hand. Right? So keep the problem definition in mind, and we'll go forward with that model definition, how we will define such model which will have two outputs, and then you will use the functional API. So simple inputs will define with Keras, let's say 28 by 28 image that is standard for your NIST dataset. We are flattening this using this flatten keras.layers.flatten Keras API. Again, we are using all the inputs up there. You can see first dense layer we are defining, which is dense layer, which is 120 output using activation ReLU function. Second dense layer, it is using 10 outputs and activation. So 10 outputs you can see here. This dense layer output is essentially will classify which digit is it. So we need 10 classes to classify. So 10 class and activation softmax function we are using because we need to classify in the end, because this will convert the logits into your predictions. And name is category output. So category of the digit that we have defined now this layer. You can name one layer. So this is just such use case where you can name the layer and you can see the layer definition with this name. Now here we are creating two output layers, one output layer for the category output and another layer for left right output. So there is just one prediction output will be there because that will give you the sigmoid activation, and with this sigmoid activation we can get whether this is just binary classification we are doing here, right? Whether it is being written in left hand or right hand. So two heads we have defined. Now here we have defined the layers as functions. Now we will use these to call on the inputs. So now we are calling them, right? So X is flattening the inputs. So the input is flattened here because this is the fully connected layer we are using, dense layers. X equal to dense 1. So first dense layer. Then output 1 is taking this X as input and doing the 10 outputs. And this output 2 is taking this layer, basically this output of this layer. So same output is going to two heads and giving two outputs, right? So this is the important thing that in the function call functional API we can do it. This is the thing that I wanted to show you. Then you can define the module, headers.module inputs. One input we have, input equal to inputs, output equal to. Now you can see we are giving the output list here. So one model we have created now which has multiple outputs. So we are giving one list of outputs here, outputs 1, outputs 2, name equal to MNIST model. So you can define one model. So this is the name of the model. If I see the model summary, what I will see is that input layer, this size, flattened layer, this size, dense one layer with this number of parameters, flattened one, which is the name, but category output 1. So you see this name here, category output dense layer and category left right output dense layer. So these are the two output layers we have created, and so total. So this is the model definition, model summary, whatever you call it. Then we are defining two losses because two heads we have. So for the softmax for this category loss, category output, we have this cross entropy loss, sparse categorical cross entropy loss from logits equal to false because we have defined the softmax activation. If you did not define the activation here, then you need the logits. So logits are the outputs directly coming from the neurons. Now loss 2 is essentially again binary cross entropy loss because we are doing the binary classification. Optimizer we are defining, metrics we are defining, what metrics we want to see, accuracy we want to see. Two losses, one loss is for category output and second loss is for your left right output. So for two output layers we have these two losses. We are comparing the model with this loss, whichever we have defined here with this optimizer and with this matrix. As simple as that. And we are training the module here. So basically, we are creating the data set here. So keeping the chaos.data sets as a source, we are taking the MNIST data set, creating train test modules, and then we are unpacking and normalizing the images here. Then we are creating the two classes. Let's say we are creating the two classes. Let's say greater than 5 will have written as, let's say, 1. Okay, so that is right-handed, and less than 5 is left-handed, let's say. Okay, so you can see here, so all these digits 500040 but 9161. So all these are written in right hand and these are written in left. So now our class levels are being created. Then we are going into training to just call feed with this train function, train data set. This number of the epochs, batch size, levels 2. So now we are getting the outputs here for the accuracy loss and for different epochs. And we are doing the predictions in the end. And this prediction is essentially calling on the test. And how many predictions we are doing? 2 predictions. First prediction is for your left hand right category and then left hand right hand. And let's say we are taking the first 20 data and checking what is the maximum prediction for that and what is the left hand and right hand prediction for that. Printing the data, the levels with let's say category and the levels for your left hand right. So all the digits have been successfully categorized. So these are the predicted labels and predicted labels for the left hand right hand. You can see 1 is for your 7, 0 is for 2, 9, 5, 1. This is wrong prediction. But again, anyway, so you have seen how you can use functional API to simply define your module with different number of outputs, and you can train the module and extract the predictions and do so. As simple as that. So if you're doing transfer learning or maybe multi-head or multi-stage training, you are creating the pipeline. This is the best way to go using functional API. So with this functional API, we will close this session and we will move towards the question answers. Thank you. Okay, so let me expand the question session. Okay. Let me read out. Okay, I do not see questions. Okay, yeah. So a few of them have been answered already. So we have in host one port, the programmer needs to explicitly give the port number. Yes. So yeah, in this case, you need to give the port numbers which you are using for the communication, right? So that you have to give. Okay, so almost all the questions have been answered. Okay, so yeah, if we have further questions, we can discuss this now. Okay, yeah, we'll wait for a few seconds and yeah, all the answers are correct. So I think do not need to discuss them. A few more questions are coming here. Is it possible to share GPU between multiple VMs? It is possible. Yes, it is possible. You can see. Okay, so basically, what you are talking about. I mean, what do you mean by VMs? So if you're having completely different ways altogether, yes, you can share them. Also for the same machine, if you're asking for the same machine, the GPU can be shared. Uh, can the quantum of distribution be known beforehand? T use distribute. Can the quantum of distribution be known beforehand? What do you mean by quantum of distribution? That means if you are asking the size of the variables that you want to share, Yes, that you know what is exact size of the distribution. So in the model definition, you will see the model summary, right? So in the model summary, you can see how many parameters are there. From that parameters, from those many number of parameters, you can now extract the size of the total number of variables will be actually defined, because all those number of parameters will have, now depending on the data type that you are using, and all the parameters will have gradients calculated, and you can calculate the total size that will be distributed, right? So you can know beforehand. What is input pipeline? So input pipeline is essentially so before pipeline, you need to understand what is input first, right? So input is essentially that for the data you need to get the input through several stages of let's say read, open, then transformation, and load, right? So all these are the stages of input of your data. And then pipeline means you just stack up after the another the stages depending on the availability of the resources. Efficient stack up. Okay, that is the pipeline you want to do. Now, if you do not know, you will do the sequential execution, because they are you are not aware of what kind of stack up you can do, right? Now, if you are aware of different strategies of, let's say, pre-patching, or maybe if you are doing batch processing for your, or batch transformation, you can do batch mapping or vectorized mapping. So depending on the use cases, you can use different pipeline strategies. In the case of sharing GPUs by two virtual machines, is it possible to use GPUs simultaneously? Simultaneously, what do you mean by simultaneously? Is it at the same time you will be using? Of course, their usage will be interleaved. Okay, you cannot use the same. So same training module cannot run for this for the same from the same VMs, right? So of course they can be shared, but depending on the processes, the availability of the processes, it will be interlinked. Okay, as simple as that. Okay, yeah. Uh, yes. Okay. We can wait a couple of more minutes to get some more questions if you want to have. Okay, another question we have now. While doing a training process, can a GPU be based on real-time data processing as well? Yes, indeed. Uh, so real-time data is basically the stream of data that you are accessing from, let's say, I don't know, maybe from your IT devices, or from the fleet of servers that you want to access the log from. Now, the training, if you want to train from your stream data, so basically the input stages, the pipeline of input stages that you have seen so far, all these are done by the training, by the streaming of the data from, let's say, even if you have a batch data that is available, that data is streamed through the pipeline, and then it is being loaded. So you can define the time window, like how much time for that data will be loaded, and you can access the stream data from your remote servers or maybe your IT devices, and then you can load it accordingly, and then you can feed it into the training modules. So that is that just how you define the ETL pipeline. Okay? So here the extraction will be from your remote sources or your IT devices, depending on the stream source that is available. So real-time data you can process. How you can define interleaving of GPU? That will be already be taken care of by the OS that is running your processes. Okay, so interleaving will be automatically done. Okay, good. Yeah, couple of more minutes we can wait for to set of questions. I think some interesting questions we have today. This is good. Uh, Okay, so if you don't have further questions, then we can close the session here. Thank you for the questions, and I really enjoyed the session. See you in the next day. So we'll have one more class for the TensorFlow, and we'll see some more of TensorFlow in the next class. Thank you.